For the next few minutes, you're going to discover something hiding in plain sight every second of your life. The true nature of light. Not the simplified version taught in school, but the deeper reality that explains how you see, how the universe communicates, and why the world around you is far stranger and more beautiful than it appears. By the end of this video, you will understand what light really is, how it travels through space, and why modern physics completely changed our understanding of reality itself. Before we begin, make sure to subscribe to the channel and click the bell icon so you never miss clear, fascinating explanations that make complex science simple, meaningful, and truly enjoyable to understand. Now take a moment and look around you. Everywhere you look, there is light. You see objects, colors, shapes, and movement because light enters your eyes. It feels obvious, almost too simple to question. But pause for a second and think more carefully about what is actually happening right now. At this very moment, light from every object in the room is traveling outward in all directions simultaneously. When you look at a chair, light reflected from that chair reaches your eyes. At the same time, light reflected from you travels toward the chair. Light moves everywhere at once, crossing paths endlessly, overlapping in the same space without confusion or collision. This raises a deeply strange question. If billions upon billions of light rays are moving through the same space in every direction, why doesn't everything become a chaotic blur? How do you still see a sharp, clear image instead of total visual noise? And visible light is only a tiny part of what is happening. Right now, radio broadcasts are passing through this room. Television signals, heat radiation from your body, radar signals from aircraft, and even energetic radiation arriving from deep space are moving through the exact same space, through the walls, through objects, and even through you, all at the same time. All of these are forms of light, just with different wavelengths. That realization alone changes how we should think about reality. The room you are sitting in is not empty space filled with only visible objects. It is an invisible ocean of energy, constantly vibrating with signals and waves carrying information from across the planet and beyond. So what is light, really? The answer most people learned in school is incomplete. In important ways, it can even be misleading. The real explanation is far stranger than everyday intuition allows, and once you begin to understand it, the ordinary world starts to look completely different. Imagine sitting beside a swimming pool. People are diving in one after another. Each splash sends waves across the water. Ripples spread outward, intersecting with other ripples, forming a complicated pattern of motion. Now imagine a tiny insect floating quietly at the edge of that pool. It cannot see what is happening. It can only feel the water pushing against it, waves arriving from different directions at different rhythms and strengths. Could that insect figure out what is happening across the entire pool just from those waves? Could it determine where someone jumped in, when it happened, and how strong the splash was? It sounds impossible, but in principle, all of that information exists within the waves themselves. That is essentially what your eyes are doing right now. The light reaching your eyes behaves like waves spreading through space. Except instead of moving across a flat surface like water, they move in 3 dimensions. Waves travel outward, overlap, and cross through one another in an incredibly complex pattern. Your eye, however, is only a tiny opening, a small detector sensitive mainly to waves arriving from specific directions. By adjusting where you look, you change which waves enter that opening. From this enormous chaos of overlapping waves, your brain reconstructs a clear image of the world. Somehow, from a tangled network of vibrations filling space, you can determine distance, shape, motion, and detail. Even more remarkable, while you are looking straight ahead, someone beside you can observe something entirely different at the same time. The same room contains countless streams of light information, yet each observer extracts only the portion relevant to their viewpoint. What is really happening is not a collection of tiny arrows shooting through space, but something far more subtle. Vibrations in electric and magnetic fields. Space itself is alive with motion, constantly shaking with invisible activity. Most objects simply ignore these vibrations. Your eyes, however, are specialized instruments evolved to interpret a very narrow range of these waves. And that narrow range, the tiny slice we call visible light, is only the beginning of a much bigger story. The waves your eyes detect represent only a very small portion of what actually exists around you. To understand this, return to the image of the swimming pool. Some waves on the water are large and slow, rolling gently across the surface. Others are small, quick ripples moving rapidly outward from each splash. If our imaginary insect could only sense waves of a certain size, it would experience only part of the activity happening in the pool. Your eyes work in exactly this way. They respond only to waves within a narrow range of sizes or wavelengths. These wavelengths are incredibly tiny. Everything you see, every color, every object, every face, exists within this extremely limited window of the electromagnetic spectrum. But what about waves longer than those your eyes can detect? Those longer waves are still light, just beyond your vision. They appear to us as heat, known scientifically as infrared radiation. You cannot see infrared light, yet you constantly feel it. When you stand near a warm stove or feel sunlight heating your skin, you are experiencing infrared waves transferring energy to your body. Some animals, however, are equipped to detect these longer wavelengths directly. Pit vipers, for example, possess specialized organs. In complete darkness, they can detect the body heat of a mouse and accurately strike their prey. To them, the world includes patterns of warmth. As wavelengths grow even longer, they become radio waves. These waves can stretch from centimeters to kilometers in length. At this very moment, while you sit watching this video, radio signals from countless broadcasting stations are passing through your room. Even stranger, when these individual particles, later called photons, were sent through the double-slit experiment one at a time, the interference patterns still slowly formed. Each photon seemed to interfere with itself, behaving like a wave spreading through multiple paths simultaneously, before arriving as a single localized event. This result shattered the simple categories of wave and particle. Light was clearly not behaving like ordinary objects. Something deeper was at work. Something that forced scientists to rethink the very foundations of physics itself. So which is it? Is light a wave or is it a particle? For a long time, scientists tried to force light into one of these familiar categories, but the deeper experiments went, the clearer it became that neither description was fully correct. Light behaves like a wave in some experiments and like a particle in others, yet it never completely fits either picture. The uncomfortable truth is that light is not something we encounter in everyday experience, so our everyday language struggles to describe it. Photons, the individual units of light, are real. You can count them. Sensitive detectors register their arrivals one by one, producing measurable clicks. The brightness of light depends on how many photons arrive each second. But these photons do not travel through space like tiny bullets following a single path. Instead, their behavior follows the rules of quantum mechanics, a framework that challenges our intuitive understanding of reality. When a photon moves from one point to another, it does not simply choose one route. According to quantum theory, it explores all possible paths simultaneously. This idea sounds almost impossible at first, yet experiments repeatedly confirm it. The photon behaves as though it spreads out like a wave, sampling every possible route before finally being detected at a single location. The famous double-slit experiment demonstrates this perfectly. When photons pass through two narrow openings without observation, an interference pattern appears. But when scientists attempt to measure which slit the photon passes through, the interference pattern disappears. The photon suddenly behaves like a particle traveling through one slit only. Nothing about the photon itself changes. What changes is the type of question being asked through measurement. This is one of the most profound lessons of quantum physics. The photon does not decide to become a wave or a particle. It is always a quantum object. Our measurement determines which aspect of its nature becomes visible. When we ask a wave-type question, we observe wave-like results. When we ask a particle-type question, we observe particle-like outcomes. Reality responds to how it is examined. This is not philosophy or speculation. It is the result of precise experiments repeated countless times. Nature itself operates in a way that defies simple classical descriptions. Light is neither a wave nor a particle in the ordinary sense. It is something deeper, a quantum phenomenon that remains fundamentally different. Yet another mystery appears when we consider how light travels. If photons explore many possible paths, why does light usually appear to move in straight lines? Why does it reflect from mirrors at predictable angles and bend in consistent ways when passing through materials like water or glass? The answer lies in a remarkable principle discovered in the 17th century, known as Fermat's principle. It states that light follows the path that requires the least time. At first glance, this sounds simple, almost obvious, but its consequences reveal a surprisingly elegant logic underlying the behavior of light. In open air, light travels at a constant speed. The shortest distance between 2 points is a straight line, so the path of least time is also straight. When light strikes a mirror, it reflects at equal angles because that specific path allows it to reach its destination in the shortest possible time. That is why light appears to move in straight lines under normal conditions. Geometry alone proves that any other angle would take longer. Things become more interesting when light moves between different materials. In water, for example, light travels about 25% slower than it does in air. Imagine trying to rescue someone standing in the water while you are on land. Because you can run faster than you can swim, the quickest route is not a straight line. Instead, you run farther along the shore before entering the water, minimizing the time spent moving slowly. Light behaves in exactly the same way. When it enters water from air, it bends, a phenomenon known as refraction. Rather than traveling straight, it adjusts its path to spend more distance in the faster medium and less in the slower one. The bending angle follows a precise mathematical relationship called Snell's law. But Fermat's principle explains why that law exists in the first place. Light is always optimizing travel time. Once this idea is understood, many familiar optical effects suddenly make sense. Consider the shimmering illusion of water on a hot road during summer. As sunlight passes through layers of air at different temperatures, its speed changes slightly. Hot air is less dense than cool air, allowing light to travel faster. Instead of moving straight downward, light curves through regions where it can move more quickly, eventually reaching your eyes from unexpected directions. Your brain interprets this bent light as a reflection, creating the illusion of water where none exists. Even sunsets are shaped by this principle. When you see the sun resting on the horizon, it has already dipped below it. Earth's atmosphere gradually changes density with altitude, causing sunlight to curve as it travels toward your eyes. The atmosphere bends the light, allowing you to see a displaced image, a visual echo of the sun's true position. Understanding light's preference for paths of least time reveals that what appears simple on the surface is actually guided by deep physical laws operating invisibly around us. And these same principles allow humans to build powerful tools that shape and control light itself. Once scientists understood that light always follows the path requiring the least time, an extraordinary possibility emerged. If we could control how long light takes to travel along different routes, we could control where light goes. That single insight led to one of humanity's most powerful inventions, the lens. Imagine you want light leaving one point, call it point P, to arrive precisely at another point, P prime. Some light rays naturally travel straight between those points, but others leave at angles, traveling longer distances. If light always chooses the quickest path, then only the shortest route should matter. So how do we convince light traveling along many different paths to arrive together at the same destination? The solution is surprisingly elegant. Instead of forcing light to change direction directly, we change how fast it moves along different parts of its journey. Glass slows light down compared to air. That means if a ray travels a longer geometric distance, we can compensate by allowing it to pass through more glass, slowing it just enough so that its total travel time matches the shorter paths. When all possible routes take exactly the same time, the light reinforces itself at a single point. That is focusing. A lens, therefore, is not simply bending light randomly. Its curved shape is carefully designed so that every ray traveling through it, whether near the center or near the edges, arrives at the focus simultaneously. The middle of the lens is thicker because rays traveling straight need additional delay. Rays entering near the edges already travel farther, so they pass through thinner glass. The shape equalizes travel times, guiding light naturally toward one location. The same principle applies to mirrors. Suppose astronomers want to collect faint starlight traveling billions of miles across space and bring it into sharp focus. A flat mirror would scatter those rays in different directions, but a curved mirror shaped like a parabola ensures that all incoming parallel light rays reach a single focal point at the same time. This is why large telescopes use precisely shaped parabolic mirrors. The famous 200-inch telescope at Palomar Observatory operates using exactly this idea, gathering tiny amounts of distant light and concentrating them into images detailed enough to reveal galaxies far beyond our own. Every optical instrument you have ever used, microscopes, cameras, eyeglasses, telescopes, works by manipulating travel time. Engineers design shapes and materials that slow some rays, speed others relative to the path taken, and ultimately guide light toward desired locations. What appears to be simple bending is actually a delicate balancing act involving time itself. But this realization leads to an even deeper and more unsettling question. How does light know which path takes the least time? Does it somehow test nearby routes before deciding where to go? Classical physics struggled with this question because it imagined light as traveling along definite rays. Quantum physics, however, provides an astonishing answer. Light does not choose a single path in advance. Instead, it effectively samples all possible paths between 2 points. Imagine placing a radio wave source on one side of a barrier with a slit and a detector on the other side. When the slit is wide, radio waves mostly travel straight through. The waves interfere with themselves along nearby paths, canceling out most sideways motion. Now gradually narrow the slit. Something surprising happens. As the opening becomes extremely small, waves begin spreading out more widely. The detector placed to the side now receives stronger signals. Why? Because with fewer available paths to compare, destructive interference decreases, allowing the waves to spread. Light is constantly interacting with nearby possibilities. You can observe a similar effect yourself using visible light. Find a distant bright point like a street light at night, or sunlight reflecting from a shiny surface. Hold 2 fingers close together in front of one eye and look through the narrow gap. As you slowly squeeze your fingers closer, the tiny point of light stretches into a line. If you look carefully, faint colored bands appear along its edges. This pattern occurs because the light spreads out after passing through the narrow opening. It is direct evidence that light behaves like a wave exploring nearby paths, rather than a rigid ray traveling straight ahead. What is truly happening at the deepest level? Modern quantum theory reveals a remarkable truth. Light consists of photons, detectable particles, whose motion is governed by probabilities rather than fixed trajectories. For every possible path between 2 points, nature assigns a mathematical contribution, often seen as a rotating arrow. Paths with similar travel times reinforce each other, while others cancel out through interference. This is why light appears to follow a single efficient route. It is not that other paths are forbidden, their effects simply vanish. We perceive a simple straight line, but it's actually the result of nature's immense hidden calculation. Once you see light this way, the familiar world transforms into a deeper quantum behavior of reality itself. Light explores every path, revealing the hidden complexity of our universe. The same reasoning reveals why light spreads when passing through narrow openings. When many nearby paths are available, interference cancels motion in certain directions, guiding light primarily forward. But when the opening becomes extremely small, fewer paths exist for comparison, and cancellation weakens. The light then spreads outward more noticeably, producing diffraction patterns. This behavior is not an exception to straight-line motion. It is a deeper explanation of when and why straight-line motion emerges. At this point, the relationship between wavelength and behavior becomes important. Light exists in many different wavelengths. The longest wavelengths, stretching from meters to kilometers, are radio waves. Because their wavelengths are so large, they easily bend around obstacles and pass through walls. Shorter wavelengths belong to microwaves, used in radar systems and microwave ovens. Still shorter wavelengths form infrared radiation, which we experience as heat. Every warm object emits infrared light. Although invisible to your eyes, this radiation fills the environment, constantly transferring energy between objects. Then comes the narrow band of visible light, the only portion directly detectable by human vision. Blue light has shorter wavelengths and higher frequencies, while red light has longer wavelengths and lower frequencies. The colors you perceive are simply your brain's interpretation of different wavelengths interacting with specialized cells in your eyes. Beyond visible light lies ultraviolet radiation, energetic enough to damage skin cells and cause sunburn. Even shorter wavelengths produce X-rays, capable of penetrating soft tissue and revealing the structure of bones. At the extreme end of the spectrum are gamma rays, generated by radioactive decay and violent cosmic events. Despite their differences, all these forms are fundamentally the same phenomenon, oscillations of electric and magnetic fields. This carries an astonishing implication. The room you are sitting in is filled with electromagnetic activity across the spectrum. Radio signals from thousands of transmitters pass silently through the air. Infrared radiation flows from every warm surface. Visible light reflects endlessly between objects. Ultraviolet rays arrive from the sun, and high-energy particles from distant galaxies occasionally pass through the atmosphere. All of these coexist without interfering with one another because they differ in wavelength and frequency. Space is not empty in the way we usually imagine. It is a dynamic network of vibrating fields, constantly carrying energy and information. Reality depends as much on what we are able to detect as on what actually exists. What is light? It is not purely a wave, and it is not merely a particle. It is a quantum object whose behavior reveals itself differently depending on how we interact with it. When unobserved, photons explore many possibilities simultaneously, interfering with themselves. Only when measured does the outcome appear as a single, definite event. This dual nature explains why the world appears orderly, despite the invisible complexity surrounding us. What you perceive is only a carefully filtered slice of a larger physical world. The apparent simplicity of everyday vision hides an intricate structure governed by quantum laws. The clarity you see is the result of extraordinary organization. The universe is far richer than our everyday intuition suggests. Understanding light is the first step to understanding the cosmos itself. Understanding light changes how we view nature itself. The straight lines, reflections, refractions, and images we take for granted are not basic rules imposed on the universe. They are consequences arising from deeper principles. Nature does not instruct light to choose the fastest path in a conscious sense. Instead, all possibilities exist together, and the laws of interference ensure that only certain outcomes remain visible to us. This realization carries a quiet kind of beauty. Human intuition evolved to understand solid objects, stones, trees, and moving bodies. Yet the universe at its most fundamental level operates according to rules far removed from ordinary experience. Physics expands our intuition, allowing us to grasp realities that no human sense was designed to perceive directly. Right now, as you watch and listen, an invisible ocean of electromagnetic waves surrounds you. Signals from across the planet and energy from distant stars pass silently through the same space you occupy. From that immense complexity, your mind constructs a stable and meaningful picture of the world. That alone is extraordinary. And perhaps that is the true lesson of light. The universe is not only stranger than we expect, it is stranger than we are naturally prepared to imagine. Yet through careful observation, experiment, and mathematics, we learn to understand it anyway. That pursuit, the effort to see reality as it truly is the heart of physics. And it reveals a world far more beautiful, subtle, and connected than appearances ever suggest.